Hello, advanced algebra students. Better add that in there. Welcome back to another video lesson as we continue to explore sequences. Today we focus a lot on geometric sequences and the application of them to real situations, things that are happening. One quick reminder down here. Again, many tests scheduled for Monday, April 12th. You are allowed your calculator. So please remember, these videos and the practice problems are all in preparation to help you be ready for that mini test. Very quickly, let's review what we did yesterday. We gave you two different formulas. A recursive formula, meaning I need that first term or I need the previous term in order to figure out the next couple of terms. Recursive, right? It has to have a repeating pattern. So we need g of 1, that's that first term. We need r, the constant ratio, times whatever the previous term was. We can only use this as long as we're looking for like the second term and beyond, right? N has to be greater than or equal to 2. So if you're asked to write a recursive formula, it needs to look something like this. Right, and here's that example. Here was our first term, which was 4. They multiplied by 3, so that's that common ratio. So we're starting at 4, 3 times the previous term, as long as we're starting at the second one. Recursive. Probably a little bit more difficult to use if we're finding like that 100th term and so on, but it's there. Then we had the explicit formula, a lot more user-friendly to find that 100th or 50th term, where we have g sub 1, that's the first term again, first term in the sequence, and then we're multiplying by r, that common ratio, to the power of n minus 1. So if I'm looking for the 100th term, it's 100 minus 1, or 99. And again, same exact setup, first term multiplying by 3, so it just changes the way that that formula looks like. If you're ever asked to write the explicit formula, it should look like that. All right, so if you didn't get those down, you want to make sure that you have them down today. Now let's put some of those a little bit into practice and just review. Find the first 6 terms. Let me blow this up a little bit larger. Find the first 6 terms of this geometric sequence. Why don't you pause the video here and see if you can't find the first 6 terms. All right, g of 1, they already give us, they tell us the first term is 5. And then g of 2. Right? This means we do 4 times the previous answer. So in this case, 4 times the previous answer, 4 times 5, is 20. My mouse does not want to cooperate. There we go, 4 times 5. So that's 20. G sub 3. We take the previous term, or I'm sorry, 4 times the previous term. 4 times 20 is 80. So hopefully you can see we're just multiplying by 4. That common ratio here is going to be 4. G of 5 is what, 1280? 4 times, that's 1280. And then G of 6. This one I can't really do in my head. So this is why calculator is going to be allowed. 5,120. Now the question becomes, how can we take all of that information and turn it into the explicit formula? The explicit. Well, remember, the explicit just lets us generalize this formula so that I can find any term by taking the, the first term, which was 5, and multiplying by the common ratio raised to the power of n minus 1. To that power of n minus 1. So we can turn that recursive formula into an explicit formula, which again allows us to find like the 20th without having to go through all of those steps. Here's another one. Find the first, 5th, 10th, and 20th terms of this sequence. A sub n equals 3 times negative 2 to the n minus 1 power. Now, notice, they give you the explicit formula. Why would they probably give you that? Well, because they're only having you find certain terms along the way. Again, if I want to find the 20th term, I don't want to need to find the previous 19 to get there. So let's figure out what is a of 1, the first term, right? What is that first term? Well, remember, in the explicit formula, this first number right here, 3, represents that first term. The common ratio is my R value right there, -2. So now if I want to find the fifth term, I'm going to do 3 times -2 to the power of 5 minus 1, right? I'm looking for the fifth term, so I take away 1. 3 times -2 to the fourth, and then I've got to calculate that. Now be careful. There's a common error that sometimes occurs in here, and I'm just going to try and enlarge the common error alert here. A lot of times what I have seen, and historically this is speaking, we forget that when we have subtracted and have 2 times 5 to the power of 9, we multiply the 2 and the 5, and then take 10 to the 9th. We got to remember our order of operations. Okay, so in this case, only -2 is being raised to the fourth power. -2 times -2 times -2 times -2 is 16, and 16 times 3 is 48. So the fifth term, the fifth term is 48. What about the 10th term? Well, if I'm looking for the 10th term, we're going to do 3 times -2 to the 10 minus 1, which is 9. So 3 times -2 to the 9th. -2 to the 9th. So -2 times -2 times -2, and so on, right? So -2 to the 9th power is -512 times the value of 3 out front, the first term, -1536. And then we've got to find the 20th. So a of 20th, the 20th term. Once again, same setup, 3, -2, and instead of plugging in 20, we actually do 20 minus 1, which is 19. So -2 to the 19th power is -524,288 times 3, gives us a final value of -1,572,864. You can double check that on your calculator if you would like. No, I don't have that memorized. I did it on my own calculator. So again, this explicit formula is so much more helpful to get to that 20th term. I didn't want to have to do all the 19 previous ones to figure it out. Okay, that's what we use explicit for. Now, how does this apply maybe to some different story problems? Right, so imagine you have maybe a bouncy ball, tennis ball, something like that, and you're dropping that ball from a height of 12 feet. Every time you bounce that ball, it's going to bounce back up to 90% of its previous height after the bounce. Notice a bounce is counted once it hits the ground. So here's the first bounce, and it bounces back up, and then here's the second bounce. Right, so this is our height 1. A little hard to see. Height 1, height 2 is getting a little smaller, height 3, and so on. If we're to write an explicit formula, H sub n, what information do we need for an explicit formula? Well, we need the first term, or the first bounce, and we need that common ratio. So be careful here with this first term. The ball is being dropped from 12 feet. That's its starting height, or what we might call the y-intercept. So that's technically not the first term. That's 0, 12. We need to know what is 1, the first bounce, and its height. We have to calculate that. If it starts at 12 and it bounces back up to 90%, we got to use the decimal form here, 90%, we get a value of 10.8. So our first height, our first term, is going to be 10.8. So we've got to be careful with some of our story problems and what information they present to us, because that first term happens to be after the first bounce in this case. What's the common ratio? Well, the common ratio here is 90%, or we will use 0.9. Meaning we can write an equation, and in this case they want us to use h, so h sub n equals our first term, 10.8, times the common ratio, which is 0.9, to the power of n minus 1. And that allows us to find the height of this ball after n number of bounces. So find the height of the ball after the 6th bounce means they want us to calculate it that 6th time. So 10.8 times 0.9 to the power of 6 minus 1 means I'm going to use it to the power of 5. I'm going to go back to my calculator here and take 0.9 to the 5th power, which is 0.59049. Multiply that by 10.8, and the height of the ball will be 6.3772. Let's read the directions. Round your answer to the nearest 10th. So that's this spot. The 7 is going to make it go up to 6.4, and my label should be feet. So the trickiest part with some of these applications in terms of story problems are making sure you understand where that first term is or where it happens. If you have any questions, please make sure that you reach out. Otherwise, until next time, everyone, stay safe.